All right, so we are going to start talking about matrices. All right, so what is a matrix? It's just a way to express data, all right, as like a table in a way. It's similar to a table, um, where each column is going to have something in common and each row is going to have something in common. So a matrix is defined as a rectangular array of numbers enclosed in brackets. So if you look at the bottom of the page where it says A equals 6, 10, 30, 24, 14, 20, that's an example of a matrix, all right? So data from a table could be represented efficiently in a matrix, and conclusions about the data could be drawn after using matrix operations. So what are operations? Just like you can add, multiply, divide, subtract numbers, you can also perform operations similar to that with matrices, but it will work a little differently. All right, so here's an example of where you use a matrix. So we have two club soccer teams, Wildcats and Falcons, and they need new equipment. And the table shows the needs for both teams. So notice how each column represents a different team and each row represents a different piece of equipment. So the way that table is there, the 6 means the Wildcats need 6 goals. The 24 means the Falcons need 24 balls. And if you added 14 and 20, that would represent the total number of jerseys that both teams need. So just like an organized way of representing this table. And when you put it as a matrix, notice there's less words, and now it's easier to do math with them, to perform operations. So that table can also be represented by matrix A. So we always name matrices with a capital letter. You know, you can name whatever letter you want. So in this case, we're going to use A. And notice how it's the same data, it's just written a little more simply, where row 1 goes, so rows go across from left to right. So row 1 would be 6 and 10. Row 2 would be 30 and 24. Row 3 would be 14 and 20. And row 1 represents goals, row 2 is balls, row 3 is jerseys. Column 1, columns go up and down. So I think of like a column in architecture, like going up and down, like holding something up. That would represent Wildcats. The second would be Falcons. So first, some vocab. So matrix A has blank rows and blank columns. So rows, like I said, go left and right. So that'd be row 1, row 2, row 3. So matrix A has 3 rows. Columns go up and down. So there are 2 columns, right? And we only count the ones with the numbers in them. So I think one thing, a lot of things in math are alphabetical, not this. When we express matrices, rows, and columns, we always put the rows first and then the columns second. So I always think of like RC Cola. I don't know if you ever had RC Cola. It's like a knockoff brand for like Coke and Pepsi. You find it in like cheap pizzerias, or like they used to have it at like this place where we used to go rollerblading when I was a kid. RC Cola, like for birthday parties and stuff. RC, rows, columns. Rows first, then columns. That's important. I'm only telling you that little story because it's important to remember. Rows come first, then columns. So when it asks you to find the dimensions of a matrix, remember 3 rows, 2 columns, you're going to express it like this: 3 by 2. And it's read like this: 3 by 2. So you actually write it out. But that's how you say it out loud. You don't say 3 times 2. You say 3 by 2. So that's a 3 by 2 matrix. All right, and that's called a rectangular matrix, which you could probably figure out. It looks like a rectangle. And we will see other types of matrices. Sometimes they're square matrices, but just like in geometry, like all squares are rectangles, but not all rectangles are squares. Same thing with matrices. We could have square matrices that are also rectangular, but you could also have rectangular matrices that aren't square matrices. Each value in the matrix is called the entry in the matrix. So if I want to know what the entry was in the first row and first column, it would be 6. So like that value, based on the position of wherever you're asking about, is called the entry. All right, and then just like we express location of our homes with addresses, it's also called that in a matrix as well. So the address, very hard to write. I should type it out. So the address of an entry is its location in the matrix, expressed by using lowercase matrix letter with the row and column as subscripts. So whereas this capital A represents the whole matrix, lowercase a followed by 2 digits represents like one element and its location. So A12, that would be like A, the element of the first column. So right here, second row. So it's going to be 10. So that those little numbers next to the lowercase letter, that tells you the location of each value. Okay. And if the number of rows is equal to the number of columns, then that would be a square matrix. So I'm sure we'll see examples of those, but that's what goes here, square. All right, so an example of a square matrix real quick would be like 1, 2, 3, 4. It's got 2 rows, 2 columns, it's a square. So in this example, what are the dimensions of M? So you would first look at the rows, so go left to right. 1, 2, 3 rows, so it's going to be a 3 by something. And then 1, 2, 3, 4 columns. So it's a 3 by 4. Now, if it asks you for a specific entry, what's M3 of 2? So that's third row, second column. All right, that's going to be 0. And then 0 appears at 2 different addresses. So we know it's going to be at M, lowercase m, because that's the name of the matrix, 3 by 2, because we just did that. But then also here, that would be at M. Wait a minute. I messed up. Let me backtrack for a second. I apologize. I don't know what I was thinking. 3 by 2. All right, that would be. So I wrote the thing right, but I circled the wrong thing. So that would be third row, second column. So it would be 11. My apologies. All right, so 11 would be the third row, second column. I don't know why I made that mistake. My bad. So it's right there, 11. Now, 0 appears at 2 different addresses. So that would be at here. So that'd be second row, third column. So that'd be M23. And then the top one would be 1 by 4. So that'd be M14, it looks like. So first row, 1, 2, 3, fourth column. All right. So that's the basics of matrices, how to tell the order, how to tell the dimensions, how to find specific entries. You can also do a lot more matrices. You can multiply each entry in a matrix by a number. That's called a scalar. So SK, like scaling it up or down, like another name for that would be scalar. So if we had like matrix like this, like 1, 2, 3, 4, and then we did scalar multiplication by like putting like a 3 out in front of it, then that means we take all these numbers inside the matrix and we multiply it by 3. So it'd be like 3, 6, 9, and 12. So that's scalar multiplication. And I apologize, it's really hard to write nicely on here. I'll try to use the calculator more. But that's what that means. All right. That is called finding the scalar product. Okay. As long as the dimensions are the same, we can add or subtract matrices. So you can only add 2 matrices with the same dimensions. And we'll look into that more later. Well, actually, real quick, if I just tried this on the calculator. All right, so if you have a TI, oh, come on, I meant to just get rid of that. Sorry, clear. Okay, so a little background on the calculator, because we're going to do that eventually anyway. If you open up, go to home screen, go to a new document, and add a calculator. All right, you could find a lot of your matrix stuff if you hit menu. There's a whole thing for it, and you could find a lot of stuff there. All right, for me, you can also find it in this button next to the 9. So if you look at like this middle part, you got a 2 by 2, a 1 by 2, a 2 by 1, and a 3 by 3. These are all like templates to plug in matrices. So like if I tried to do like a 1 by 2 and add it to a 2 by 1, it's not going to work because they're different dimensions. It's going to say dimension mismatch. All right. Now if instead I tried to add a 1 by 2 to a 1 by 2, let's say 5 and 1, right? You can add them. And the reason why they need to be the same dimensions is because you only add the entries in the same position. So like the 7 comes from adding 2 and 5. 4 comes from adding 3 and 1. Now, since we're here, you can also, if you go, like, let's say this, I'll type in, like, let's make this like 5 and 7. If you hit menu and then matrix, you can see there's a bunch of things you can do here. You can even have it like find the dimensions. So this is the dimensions. So DIM of this matrix, it'll tell you it's a 1 by 2. So if you're ever not sure of the dimensions, you can use the calculator to check that. And I can also do scalar multiplication. Like if I took this matrix here and then just did like a 5 in front of it and multiplied it by 5, then everything inside the matrix would get multiplied by 5 as well. Okay, so that's matrix addition and scalar multiplication. We can also multiply two matrices together, but we're not going to do that today. We'll spend the whole day on that. There's also called the transpose of a matrix. All right, transpose means you just switch the rows and the columns. So if this is M, then this is M transposed. So you represent transpose by putting a little T up there. Now, how do you do it without a calculator? Well, you just interchange each row and each column. So this is row 1. All right, this becomes column 1. Right, this would be row 2. That becomes column 2. And then row 3 becomes column 3. And there you go. There's your transpose matrix. Now, sometimes you want to do that like in certain word problems. If you don't like the way like it's expressed, sometimes you want to transpose it. But other times I'll just tell you straight up how to transpose it or to transpose it. And you can always check it on the calculator too. Question? Sorry, someone said something. So let's say I want to transpose this on the calculator. Let's just take this, hit that. So you can, if you do that button and you click the 3 by 3 picture, right? So if you don't see what I just did, you click on this 3 by 3 matrix, you can edit and make it any type of matrix that you want. So let's say we want like a 2 by 3. All right, I want to go just type in the entries like this, just doing random numbers. And I want to transpose it with the calculator. Type in your matrix first, then hit menu, matrix, and then transpose. And you'll see it'll be raised to the T power. Hit enter, and then it does it for you. All right. So that's all transpose means. You just switch the rows and the columns. Row 1 becomes column 1, row 2 becomes column 2. All right, so now just some rules when it comes to adding and subtracting matrices. So commutative property means you can add in any order. So multiplication of regular integers is commutative, meaning like 2 times 3 is 6, 3 times 2 is 6. But subtraction isn't commutative. If I did 2 minus 3, that'd be negative 1. If I did 3 minus 2, it would be positive 1. So not all operations are commutative. All right, when it comes to matrices, addition is commutative. So an example of that would be like, all right, let's take this matrix, like 1 and 2. So I'm just doing a simple like 1 by 2 matrix. And then add it to this matrix, which we'll say is 2 and 3. All right, that's going to equal a matrix that's 3, has entries 3 and 5. Because you do 1 plus 2 is 3, and then 2 plus 3 is 5. So you add the entries in the same address, in the same location. All right, if you did it the other way, if you did like took the second matrix and added it to the first matrix, it would still give you the same answer because matrix addition is commutative. So 2 plus 1 is 3, 3 plus 2 is 5. All right. So commutative property is true of matrices. All right. It's matrix addition. It's not true at matrix multiplication. So when we get to multiplying matrices, you can't do that in any order. If you're multiplying matrices by a specific number, like scalar multiplication, that you can do. All right. Same thing with the associative property. So if you were adding like three matrices, the order doesn't matter. So let's actually, I'm going to do this with text here because it's easier to type out. So if I was doing like 1 and 2 plus 2 and 3, and then plus like 3 and 4. I'm just making random matrices. All right, I could add these first two matrices first, and that becomes 3 and 5 plus 3 and 4. So that would be 6 and 9, right? Whereas if I did it a different way, if I added the second matrices first, so if I kept that 1 and 2 there, and then added the second two matrices, so 2, 3, 3, 4, those added together would be like 5 and 7, and then added those up, I would get 6 and 9. So that's just showing the associative property, which means if you have three things, you can perform the operation between two of them, doesn't matter which two, and then do the third operation. So matrix addition also has the associative property. So if you have three things, you can add them in any order, right? For the additive identity, all right, in math, identity means you apply the operation and it keeps its identity. So the additive identity would be 0. The multiplicative identity would be 1. If you multiply something by 1, it's going to stay the same. So with matrices, the additive identity would be a matrix with all zeros, but it has to be the same dimensions. So if I wanted to add something to this so that it keeps its identity, I would add the matrix that has all zeros in it. And that's going to keep this matrix the same. So like 1, 2, 3, and 4. All right. And then for the additive inverse, all right, in math, inverse means you perform an operation to get an identity. So sort of like canceling out. So like what would you add to a matrix to get the inverse? Like 1, -2, or -3, I'll make it up, 5 and 2. All right, so what matrix makes this just a matrix of all zeros? The additive inverse would be just take all the opposite numbers. So instead of -1, you have a 1, a 3 instead of -3, a -5 instead of 5, and a -2 instead of 2. And now if we added those, everything would cancel out. All right, so in math, inverse means like undo something. So how do you undo this +1? You add -1. How do you undo this -3? You add +3. All right, so now let's do some operations here. Oh, my bad. All right, so always, sometimes, and never. Matrices A and B have equal number of entries. A plus B is defined. All right, that you may think is true always at first, and it is true a lot of times, but it's only true sometimes. In order for you to add matrices, they have to have the same dimensions. So on the calculator, I'll show you an example like here. See, these two matrices, they couldn't add because they had different dimensions. But this matrix had 2 entries and this one had 2 entries. So it doesn't matter about the number of entries, they have to have the same exact dimensions. But like these two you can add together because they do have the same dimensions, and so they both have 2 entries. So just because they have the same amount of entries, like a 2x3 and a 3x2, they both have 6 entries, doesn't mean you can add them. They have to be the same exact dimensions. And then matrices A and B have different number of entries. Well, then that's definitely not true. So that's never true, because if they have different entries, that means they're different dimensions, and you can only add matrices with the same dimensions. So that's never true. Right? This was sometimes. And then if matrices A and B each have 4 rows and 3 columns, A plus B is defined, all right, that's going to be always true because that means they both have the same dimensions. They're both 4 by 3 matrices. All right. If A plus B is defined, then A minus B is defined. All right, that's going to be true always because subtraction is just adding the opposite. So it's still adding. So you're still allowed to do it. Like if I had like this minus that, all right, that's the same thing as doing this, where I just make this a plus and make that a negative and that a negative. So instead of subtracting 3 and subtracting 2, I can add -3 and add -2. It's the same operation. And we know that adding matrices works as long as the dimensions are the same. So same thing with subtraction. As long as you're subtracting matrices that have the same dimensions, you can do it. So this implies that the two matrices have the same dimensions. So therefore, you can subtract them. And then A plus A transpose is defined. All right, that's going to be sometimes, and it's only going to be true when you have a square matrix. Because again, in order to add matrices, they have to have the same dimensions. And when you transpose a matrix, you're switching the rows and the columns. So if the rows and the columns are the same, when you switch them, it's not going to make a difference. All right, so here would be an example of that. So let's say 1, 2, 3, 4, right? So that's matrix A. Now we want to add that matrix transpose. So 1 and 2 would now be column 1, and 3 and 4 would now be column 2. So bang, you can add those. Now, if I was adding this matrix to that transpose, well, if 2, 3 is a 1 by 2 matrix, when you transpose it, it's going to be a 2 by 1 matrix. So now the dimensions are different. You can't add them. So you can only add a matrix to that same matrix transpose when it's a square matrix. Okay. So now for these, so I'll show you a couple and then I'll let you work, and you can check all these with a calculator. So if you have a different type of calculator, just let me know and I'll help you with your calculator. So, right, C plus D, we'll do that one together. That one's pretty easy. They have the same dimensions. So you just can add the entries in each position. So like this is going to end up being a 2 by 2 because C is a 2 by 2 and D is a 2 by 2. And you can only add matrices with the same dimensions. It's going to end up being a matrix with that's also 2 by 2. So -4 plus 1 is -3. 1/2 plus 4 is 4.5, so 4.5. 3 plus 2 is 5. And -1 plus 3 is 2. So that right there, 2 by 2 matrix, C plus D. All right, B transposed. Do that one together. All right, just take row 1 and then make it column 1. All right, take this row 2 and then make it column 2. And there you go. And that's it for adding and transposing. So for 3 and 4, you would just take A, which is a 2 by 3, and then transpose it, make it a 3 by 2, and then add that to E. All right, same thing with 4. You would take E, which is a 3 by 2, transpose it, it becomes a 2 by 3, and then add it to A. All right, for 5, what you would do is you would perform these operations of like subtracting and adding, but first you would apply like the scalar multiplication. So let's do this one together, number 5. 3G. So if we look at G up here, all right, if that's G, then 3 times G is going to be 3, -15, 9, and 6. So that'd be 3 times G. And then -4H. Well, H is a 2 by 2. So we're going to subtract 4 by that. So 4 times 5 is 20. 4 times 1/4 is 1. 4 times 2 is 8. 4 times -3 is -12. And then 2C, we'll look at C. C is a 2 by 2. So if we do scalar multiplication by multiplying everything by 2, we would get -8, 1, 6, and -2. All right, so now to add those, you can use the associative property, which means you can add these two together first, right, and then add that blue one, or add the pink and the blue one first and then subtract it from the orange one. Either one would work. So if I add these two first, I would get 3 minus 20 is -17. -15 minus 1 is -16. 9 minus 8 is 1. 6 minus -12 is 18. All right, and then we can add this matrix here. It's very hard to write like this. I apologize. That's sloppy and takes forever. But what are you gonna do? All right, and then now we could just add. So -17 plus -8 would be -25. -16 plus 1 is 17. 1 plus 6 is 7. 18 plus -2 is 16. All right, and then if you want to check this with a calculator, you could just type this in. Just instead of G, put what matrix G is. Instead of H, type in what matrix H is. And instead of C, put what matrix C is. And the calculator would do all in one shot and give you that answer. All right, so yeah. Then, yeah, great question. You would just say, not possible. You can't do it. So if I said, what's B plus C? All right, well, B is a 2 by 3 and C is a 2 by 2. So you'd say not possible. So it's like, yeah, if any, it has to be the same exact dimension. So yeah, if the columns or the rows aren't the same in both matrices, you can't add them. Does that make sense? So yeah, these both have 2 rows, but since this has 3 columns, and this has 2 columns, you can't add them. It has to be the same rows and the same columns. So like for this one, like this has 3 rows and 2 columns. You wouldn't be able to add it to any of these because none of these are 3 by 2s. They're all 2 by 2s, 3 by 3s, or 2 by 3s. So yeah, you can only add and subtract matrices that have the same exact dimensions. All right, for 6, that's scalar multiplication. For 7, right, you're just subtracting them. For 8, notice the parentheses. So, the order of operations still applies. You would do what like C and D was first, like add them together and then transpose that. Whereas in 9, you would transpose D and transpose G first and then add them. So pay attention to the parentheses, the order matters. All right, and then the last one, you could treat it just like an equation. So I think I'll let you try that on your own. And then if you want me to go over it, let me know later today or next class and I will. Oops. All right, so I'm gonna pause this.